Hello and welcome to this tutorial on applying Ansys FreeFlow to model a stir tank reactor. So Ansys FreeFlow is quite a new tool from Ansys that uses smooth particle hydrodynamics, or SPH. So to start off, you can go into File and then you can create a new project, and that will basically give you this window with data. So if the data is not visible, you can go to click in view and check data so that you can see. So this is the tree that we're going to be working from, and there are different parts to it. So first I'll go to study and I'll name my study. I'm gonna just call it stir tank, and then for description I will say I'm doing study with an impeller at 5 radians per second, and basically fluid is water, and with an inlet of 60 tons per hour. So this is optional, but it's good to have some notes, especially if someone else is looking at a simulation or something like that, or for yourself to remember. So it's a useful addition to the software. It's a useful tool in the software is to actually allow you to write a description. So then we're going to modules. Modules are some of the tools that you can apply for your SPH, including some tools that you can use for post-processing. So density monitor is applied by default. I will add this one, the boundary interaction statistics, and HTC calculator. Sorry, not this one, the mass flow rate. So I'm not looking at heat transfer. I'm assuming everything is at basically room temperature. So otherwise, if I was, I would apply SPH HTC calculator. For this one, I'm using just a SPH mass flow rate, and I can actually check each of these. And then there might be options for each module that I add. So for this one, for SPH boundary interaction statistics, I will add nodal forces and stresses, no heat transfer. We could add wetting parameters, but not so much for this application. So that tells you like the wetting time on a surface, for example. And the boundary curves, you can look at things like force and torque, for example, which could be useful for what we're looking at. And for mass flow rate, I'll have to populate this with this with different surfaces. I haven't added the surfaces yet, so I will do that later. So basically it tells me, actually, if you look at in the status, that I haven't defined an inlet and outlet, or I haven't defined any inlet yet, so that's what I need to do. And basically the boundary interaction statistics require at least one SPH injection, which is what I'm going to do as well. First let's look at the physics. So the physics gives us information about the direction of your gravity, when you start applying gravity, when you end application of gravity. So for my application, I want gravity to always be a constant. It will be geometry dependent on like which direction it is oriented towards. So first I should go into geometries and import some. So I'll import some walls. The walls are basically walls that the particles my fluid is going to interact with. So you can right click geometries, click on import walls, and here I will basically use the impeller and the tank body as my two walls. So walls could be static walls like the tank body, or moving walls like the impeller, for example. So I will click open. try again. I'll open this one, and okay, so let me go back. So one thing I should mention, that the reason why it's popping up another window, because it wants to save my FreeFlow simulation file, so I'm going to actually do that. So it's, let me call tank 5 radians per second. So, and then I'll not change anything here, I'll just keep it as it is. So I have my impeller and my tank body already implemented. So if I want to visualize these walls, I can go into Windows, and I can click, and if the windows are not visible, I can just go into View and enable Windows. So I will go into Windows and click New 3D View, and here you can see the geometries that I've just added, and they are visible, so you can see the eye is open. There's no nothing crossing the eye, so that means the impeller and the tank bodies are both visible. And if you want to see the impeller inside of the tank body, we have to make the tank body transparent. So now you can see the tank body with its center demarked by a sphere, and the impeller is just this little body here. For this application, I'm only going to apply a moving frame to the impeller, not the shaft itself, but for simplicity's sake. But we could also have the shaft moving as an independent body or as part of an impeller. So basically these two are the walls. Make sure that if you go here, so into the data editors, you can see the name of the body or of the wall. It's called impeller. Motion frame, I haven't created a motion frame yet, so I'll keep this unchecked. I won't select anything. And materials, I'm just gonna leave it as default materials. Similarly, tank body, same thing. Basically, I won't apply a motion frame at all at any point for the tank body. It's a static wall. So, and then I will also add surfaces. So when we import surfaces for inlet or outlet, for example, they have to be imported separately from walls. So I will go into import surfaces, and I'll import surface 1 and surface 2 that I've created, both STL files, and copy, and then they are going to be basically my inlet and outlet. So I will actually define them accordingly. So surface 1 is supposed to be my inlet, and so I'm going to rename that as inlet, and no motion, okay. And also my surface 2 is my outlet at the bottom, so the water is going to flow from the top, drop to the bottom, and I will call it outlet. Okay, so one thing to look is, I will increase the size of this. This is the inlet that I've defined. Look at this arrow. It's saying that the reference vector of the inlet is pointing in the outward direction, which is not what I really want. I want the inlet to be pointing into the geometry. So it's the right, basically the right way would be to point inward. So I need to click on invert normal. So then now it's pointing in the right direction. Similarly for the outlet, it's pointing inwards. For the outlet, I want it to point outwards. So I'm going to the outlet, and I'm going to just invert the normal as well, so that the particles will go in the right direction. So the inlet and outlet are defined at the surfaces, but I have to actually define them somewhere else, where I will define the flow rate and so on. So let's do that now. So let's create a fluid inlet. So right click, inlets and outlets, create fluid inlet, and then I'll go into fluid inlet, and then I have to select an entry point, which is my inlet surface. So I have to link my inlet surface to my fluid inlet here, and then I have to provide a mass flow rate or a velocity. Here I will provide a mass flow rate of 60 tons of water per hour, and time is when you start and stop. When you start and when you stop, I want the flow to be ongoing from time 0 all the way to the end. And similarly, I have to create an outlet. So then if you go into outlet, I have outlet 01. I'll keep this name. So I won't prescribe a pressure, but I will enable it for SPH. And finally, I also want to make sure that I have water at time 0 already in the tank. We could either just simulate the water filling up from nothing, or we could have some water at time 0. So to do that, I can go into volumetric inlet, create volumetric inlet, and then you can click on volumetric inlet here, and then I can apply an initial velocity to it. I won't do that. I will create a certain mass, so I will add 500 kilograms of water at the beginning for the SPH. And then if you go to the region tab, I will basically select a geometry where this mass of water is going to be present in. So I will check on tank body, and you use the geometry itself to compute the tank body. So now what it's going to do is going to add a volume of water in here, and you can actually see on like the sphere here where that water is being added at. I could raise this a little bit as well, just to allow it to say not go straight to the outlet. It's going to be a big mass, and it's dependent on the volume of your geometry, of course. So basically the impeller, the shaft is oriented in the Z direction. So if I increase this by a little bit, I can actually raise this ball, which is where my mass is going to be. It's like a reference point for me. So maybe this, and then yeah, let's keep it as it is for now. And yeah, so we specify the inlets and outlets. We also need to create the motion for the impeller itself. So to create motion, first I have to go into motion frames, and in motion frames I can right click and press create motion frame. So now I have frame 01 as my newly created motion frame that I will apply to my impeller. So for relative position, I can basically match that relative position to the position of my impeller, so I have to go back to impeller to check what it is. So here I'll basically use the pivot point, so 0, 0, about close to 0, and then 0.3948 something, and then I'll just copy that number and place it into here. And basically let me increase this. So we have the relative orientation, I'll keep it as it is, and then I have to create a motion. So motions, I'll press a plus sign here, and then the default is translation. I'll change it to rotation. So a rotation, we can start a rotation, let's say what I'm going to do for the simulation is, because I will let first the water kind of settle down, and then I'll start running the impeller soon after, or kind of during. So I'll give some time for the for the water to settle down, like 0.5 seconds. Might not be enough, but let's see. And it's gonna run from 0.5 seconds all the way to the end I won't run for 1000, but this is the default value, like a large number. And for angular velocity, you can either specify the initial angular velocity or the angular acceleration. Here I want to have a fixed angular velocity, so I will write the angular velocity here of 5, and it's in the Z direction, so it's rotating about the Z axis. That's why I choose this field and not the other ones. So that is specified, and now I have to link that motion frame to my body. So I'll go back to impeller, and I'll go up here, and then I'll on motion frames, make sure you're in the wall tab, and then select frame 01, and now it's linked. Now we have a link of the motion frames. So that's all we need to do to enable this body to move, and you can verify that it is going to move properly by clicking on the preview. So if you go back to motion frames and you click preview, it's going to open up a new window, and I have to go to tank body here, coloring, and make the body transparent so I can see. And then I'll go back here, and then I'll just click on this guy here, and then you can see it's moving, right? It's moving according to what I want. So this is a nice way to preview that the motion that you specified is correct. So I'll stop this. I'll close this. So we've defined the motion, we've defined the boundary conditions, and looking back at my geometry selections collection, it's saying that the outlet hasn't been selected yet, so I have to go into outlet. I haven't selected the outlet, so click on the outlet. Yeah, so link the outlet surface to the outlet boundary. And so yeah, I specified the motion frames, I specified the body, the walls as well. Now if you go into materials, we are using water, our default fluid, which is water, so the density is 1000 kilograms per meter cubed, viscosity of 0.001, and yeah, so we can also go into physics. So for physics, I mentioned early on that we have to specify the direction of gravity accordingly. So gravity is actually in the negative Z direction for my geometry. So what I'm going to do is I'm just going to change this to match my geometry, so it's in the negative Z direction. And now let's go into SPH. So for SPH, I will use the default WC SPH, so the weakly compressible SPH, and the fluid material is going to be the default fluid, which is water, alias for turbulence type, the Cleary as a viscosity type, and surface tension type I'll keep it as none. Sound speed usually recommended is around 10 times your maximum speed. However, if you go higher, there may be more computational cost associated with it. So for this application, I'm assuming that hopefully we're going to be like 5 meters per second, or maybe more than that actually, but I'll keep sound speed at this point. It might not be enough, so this is just a trial to see what's going to happen. Also for kernel size, the kernel is quite important in SPH, so we have to specify an element size, which will tell us about the level of detail and the accuracy of my SPH particles. So for SPH, let's try an element size of 0.005 meters. So the smaller you go, the more detailed and the longer it takes to solve. We're going to use the whenland kernel type, and kernel distance factor we're going to keep at 1.5. So this is in the model parameters. There's some advanced parameters as well, so if you want to go into more detail, there's more discussion about these parameters in the FreeFlow manual. And I also didn't mention anything about the coloring tab here for the data editor. So the coloring tab is going to basically define the color of your particles as they show up. And the stride also tells us like how many particles you want to reveal in your plot. So 1 is basically you show them all. If you increase that to say 10, you're gonna have at least 1 in each 10 particles, and so on. So it's gonna actually make it like your animations faster. If you have bigger number of strides, I'll keep it as 1 as the default. And for node color, you can specify the red color, which is default. I can change that to blue to make it look more like water, or I can also change based on the property. So I don't have any properties yet at this point, but once I start running, I will have properties like velocity and so on. So basically for SPH that's good enough. So let's keep blue color. I'll keep the Larian solution on by default. That will be very important looking at visualization and post-processing. So basically I believe that's it for now. So we don't have any issues with any messaging, any messages in our status. Now let's go to our solver to define our run. So I want to define like the simulation duration. So the default here is 20 seconds. For this simulation, I'm going to keep it small, like just 4 seconds, just for demonstration purposes. And the time interval, I'll lower that to 0.01. And yeah, and for general, so I will use a GPU, and yeah, so that's basically it. So and I'll mention previously in the beginning that I created the modules, so I have to go back here and populate them accordingly. So I don't have to add anything to the density monitor or to the boundary interaction monitor. I do have to add something about for the mass flow, so that I can actually later on do some post-processing and plot the mass flow rates over time for the different surfaces. So I will add one for the inlet and one for the outlet. And that is basically it. So no messages in the status again, so that we can basically run. So before I run, I'll just save and then press start. And then the first thing it will do is it will generate the particles, and then once that is done, it will pop out some information about the number of particles generated and so on. That will disappear, and then we will start running the simulation automatically. So as you can see, these are some of the properties, the simulation summary, and it's initializing. It's specified the time step duration as well, the number of triangles and SPH elements. So basically what we can do is wait for the whole simulation to run. It can take a few hours actually. We can actually monitor the run visually by pressing auto refresh, and basically to make sure that we can see the particles, you have to go into SPH and make sure that the eye here is visible, set to visible, as well as the geometries are visible. We can make them invisible, like we can remove the tank body, or the impeller, or the inlets as well, just for visibility, or the SPH particles. Yeah, but this is like useful to observe how it's going basically. You can also look at the mass flow rates, for example, on a graph. So to do that, I can create a new time plot, and if you go into my inlet, we have the inlet mass flow. I can put it in here, and then the outlet mass flow I can put in the same plot. Now I don't have any data because it's still in the early stages of the simulation, but once I start getting data, you're gonna start seeing lines plotting. So yeah, so in the meantime, depending on computational efficiency, we could also create some tools for visualization while the simulation is running, and actually test them with some limitations. Of course, it's better to use the full power of post-processing once the simulation is fully run, but there are things that we could show during this process. So if you go into SPH and then right click, and then there are different processes that you can select. I like to use the plane to visualize, to use like a cutting plane to visualize just particles in a certain segment of my domain, or a cube, for instance, is fairly useful. We can filter based on certain properties so that we only see some particles based on, say, their velocity, and you can filter based on the range. So these are some of the key tools that we could use. So if I create a plane, for example, and it actually shows up in here already, so I already have the plane defined here, so the plane is in red. So I can actually either modify the plane directly on the viewer by dragging around, or I can basically change the vector as well as the angle. The origin of the plane can be modified as well. So there's a lot of flexibility here, and once you've defined a plane, I would first disable the Eulerian view so that I can see the particles only based on what's in the plane. And then I'll click on nodes, and the nodes are red. I will change them to blue. Press OK. So now we have just blue particles cutting basically close to where the impeller, half of the impeller is. So notice that the plane is defined for the SPH particles. We can also define planes for the geometries, for geometric entities, for example. But because it's defined for the SPH particles only, it's only applied for the SPH particles. That means the geometry doesn't get affected by it. So I have a full view of the geometry, and I'm just looking at the particles themselves. So after running my simulation for the 4 second flow time, but a few hours waiting, so I get basically these results. So this is as you can see, the particles representing the liquid water being poured into the liquid tank. So this is for around 3 seconds what the results look like. So if we go back early on, you can see that we start with kind of a pyramid sort of like shape, and then as you evolve in time, and this is kind of slow, but basically what you see here is slowly slowly you're going to have the particles sort of falling. Let me disable all the other filters that I established here. So I have a lot of user processors that I created in the meantime to better visualize everything. So you can see that the water is kind of settling down, kind of violently actually, and you can see the water being poured from the inlet as well and reaching the surface, and I can stop at any time here and visualize. So if I want to visualize the particles based on their velocity, I can go into SPH and see that the node color is set to blue as I established early on. So if I want to change it to velocity, I can go here and click on velocity, and you can see that there's higher velocity in the top, lower velocity in the bottom, and a lot of particles speed up in the very outlet of the domain and the very bottom of the domain where you have a flow outlet. And I think if I go a bit further, so you can see a lot of movement in the early stages. A lot of splashing going on, but at like after 2 seconds it kind of settles down a little bit. So I might have to it would be actually better to choose a frame motion for the impeller to start later on. 0.5 might not be enough time for the water to settle down, but you can see here it's mostly kind of settled, with some splashing, mostly from the inlet water splashing, but yeah, if you go into around 2 seconds, you can see how this looks, and it kind of the water basically moves around. The water that's being added here has a big impact on the overall mixing of water. So there are different tools that we could use for post-processing. So when we look at the water like this, it's kind of hard to see what's inside. That's why I created the plane that I showed earlier. So I created a bunch of other planes in the meantime. So planes can be like cutting or clipping. So for cutting planes, so I actually have a plane that's looking at just above the just online, close to the impeller. So I'm actually going to enable that. So first I'll disable the SPH, and I'll enable this guy. And actually I think I've enabled the wrong one. Okay, yeah. So that's actually plane 02. I moved things around a little bit. So basically, if you look at plane 02, this is an SPH plane. You can use properties that are already written in FreeFlow. You could actually create your very own. So I created a tangential velocity custom, just to look at level of circulation around the axis. But if you look at just the velocity, and here I put a stride of 50, and I'm looking at the vectors, so you can actually see the direction of the flow, and I will focus a little bit closer to the impeller, and you can see a lot of the vectors, like the vectors are getting at a higher velocity near the impeller, and there's a lot of like strong higher velocity going on in this region, which is close to where the water is being added into the fluid. So actually the water inlet seems to have a bigger impact on the mixing profile than the impeller itself. The impeller is a relatively low speed of 5 radians per second. So, and we can actually view this as a video. We can create animations, which I'll show soon how to do it. And I also, if I go back, if you look at, again, I previously showed this plane. I changed the name a little bit. So if you look at this plane, and I'll disable the previous plane and I'll enable this plane. So I don't quite have anything visible here, no edges nor nodes. Let me see, I think so. Usually if it's an SPH plane, you would have vectors in a so this is a geometry plane actually. So let's look at SPH plane. So this is an SPH plane, and I have to make it visible. So now you can see up close what we have here. So what we have here is sort of like a cutting on the middle of the tank, close to the impeller. So you can see how the water that's being added, that's being poured into the tank, has a significant impact on the flow profile. There's some speed up here close to the impeller as well, but it's heavily influenced by the water that we are adding. So before we end, I want to also mention the plots. These are useful tools. So here, as I mentioned previously, I plotted the inlet mass flow and outlet mass flow. So you can actually see that the inlet mass flow, the rate is defined here. It's actually lower than the outlet mass flow, which means I'm actually losing mass. So this is not really steady state. So I would have to increase the amount of mass flow, or modify the geometry, or play around with the design so that we could reach steady state. So, but this is not steady state. And another way you can visualize that is by looking the amount of mass that I have in the tank, amount of mass of water. So as you can see, this is dropping quite a lot over time, but not that much, but yeah, this is 4 seconds only, and it drops by around 20 kilograms. So that means we have loss of mass over time. So this is another demonstration that we haven't really reached steady state. If we do, we need to increase our flow rates a little bit more to match the outlet flow rate. So another thing that I want to point out is the ability to use cubes to do sort of like trace analysis, to look at how your fluid is moving around your geometry, and then create an animation for that. So I've created a cube already. It's called, I believe it's this one, yep. So it's cube 02, and to create that cube you have to go into your SPH. You can create processes and then create a cube, and then it's gonna basically generate a cube into the user processes. And here I specify no motion. I designed the cube to be at the inlet, so I moved it around manually to get it to move to here, to the inlet. And what I want to do with this cube is basically color the particles that come at a certain time, and visualize only these particles as they come out of the inlet and get mixed within the tank. And then we can do more analysis on that to see like how they mix, what is sort of like the residence time. I haven't run enough to look at that, but if you're doing a more in-depth analysis of this tank, for example, that could be something that we could do. So yeah, I've defined the cube here as follows, and I'm not gonna color anything, and then I'll go back to SPH. I'll right click, and then show SPH calculations, and I'll do tagging, and then I'll choose cube 2. Okay, so now you can see in calculations it has this tagging cube 02, and that's where I'm going to change basically the time which I want to use for tagging. So any particle that is within this cube at a specific time range would have a certain color. So I'm going to color from 2 to 2.1, so just a 0.1 second time range, so a pretty short amount of time. So I just want to use a few particles, not that many, and I want to study their mixing behavior within the tank, sort of like tracer, as I previously mentioned. So this is done, so the tagging is defined, and then I can go back into user processes. I will actually go back to SPH, and then I'll create processes, and I'll create a filter. So for the filter, I will filter based on the property, and the property will be tagging. So in the property limit, I will basically tag anything that's basically 1. So the tagging is going to be like binary. If it's part of the cube, it's 1. If it's not part of the cube, it's 0. So I'm just going to put 0.5, but basically this will cover particles that are equal to 1. And then coloring, I will basically make it visible. Note that the filter is defined here, and to actually I should disable the view for the other items. So I won't disable the color scales, but I will disable the plane view, and then I'll make this visible, and I will apply I'll view the particles based on their velocity, just the set of particles that come in to my domain. And you can actually see them here because I'm within the interval when the particles are tagged. So that is basically it. And then when I run, the timer, you can actually see particles as they evolve, as they're tagged. So then I finished my tagging after 2.1, so no more particles are tagged. So, and they're all colored by their respective velocities. So I'll remove this scale here. As you can see, it can be kind of slow in my computer. One thing is you could basically generate a video for that. So to generate a video, and I will stop this for now. You can go into basically tools, animation, and here I had created a video already. Let me delete these. I will go into time of 2, and then so it moved it to 2 seconds, and then I'm going to press the plus sign, and then I'll go to 4 seconds, and then press the plus sign. So here you can see that the particles that have been tagged are still, a lot of them are actually still in the tank, kind of mixing up, but some of them have already left the tank. But with this you can actually create an animation for any sort of particle dynamics. To do that, then once you have defined the first and the last frames, you can actually define more intervals here, especially if you're doing like motion, if you're moving around your geometry as well, you can do that, and it will interpolate. But here I have a fixed view of just the particles moving around, so I will export interpolation as an AVI, which is a video, and I will call this just tracer 2, and it will take some time to generate the video, but once the video is done, and you're actually seeing playing real time here. So after I ran the animation, the tracer analysis, I also ran different types of animations, created different videos. This is for the plane that's cutting, the cutting plane at the center of the tank, where you can see the impeller moving with the fluid being added to the domain. So you can see a nice animation here showing how the impeller and the fluid being added from the top affects the flow profile. You can also see here the vector for the nodes with a specific number of strides, showing like how the vectors look around the impeller, as well as close to where the water is added as well, the impact of water being added. And here is the tracer study that I was doing, so you can easily see the mixing profile and some of the particles already exiting the domain through the bottom. And finally, this is an Eulerian view. So when you do your calculations, you can actually the default mode is to do the Eulerian calculation, so it's a continuous profile, and you can actually use to see through as well your domain. Basically, it allows you to have a transparent fluid zone, and you can see basically the profile that pretty much should match closely what you have in the particle SPH view as well. So this basically completes our quick tutorial on how to set up SPH for stirred tank reactor with only water and an impeller at a 5 radians per second speed. So a lot more can be done with a more complex geometry for longer times, and I would highly recommend trying that, depending on trying this software with all of its power for both pre-processing for calculations as well as powerful tools for post-processing. Thank you so much for watching this tutorial, and I hope if you have any questions, please reach out to us, and we'll be happy to provide you some insights. Thank you so much.